Okay, this is just a quick little video of 12 questions to maybe kind of help you differentiate between permutation, combination, and maybe when you could also use the fundamental principle of counting. So I've just got 12 questions. I'm going to answer them really fast, and then maybe that'll help you clarify between the three. So this first one, a team of 8 basketball players needs to choose a captain and a co-captain. You could actually do this one with the fundamental principle of counting. So you could say, okay, I'm going to pick a captain, and I'm going to pick a co-captain. There's 8 people to choose from for the captain. You choose one, so that means there's 7 people for the co-captain. Well, 8 times 7 is 56. You could also do a permutation on this one. Order matters. Captain and co-captain, they're different. They're titles. Order matters. So you could say 8 permutation, and you're choosing a captain and a co-captain. That's 2. So that also gives you 56 outcomes. So 2 different ways to do that one. Okay, so same thing on this next one, the batting order for 9 players on a 12-person team. Okay, so since they are batting, order matters. You could do this with the fundamental theorem of counting also. So you could say, okay, batter number 1, you've got, there's 12 people to choose from. So batter number 1 would go in this spot. Then batter number 2, there would be 11. Then 10 for batter number 3, 9 for batter number 4. These are your, I don't want you to think that these are fractions. These are your batters. So let's see if I can maybe make this. So everything below here, these are your batters down here, the batter numbers. So these are all positions down here, batting positions. So the 5th spot, there would be 8. 6th spot, there would be 7 choices. Whoops. Then we've got 7, 8, and 9. So then this would go 6, 5, 4. That's a little confusing with all those numbers. But that's the fundamental theorem of counting, and you could multiply all those out. And if you did, you end up with 79,833,600. Or the easier way to do that one, I think, is a permutation. Order matters. It matters who batter number 1 is. It matters who bats in those positions. So I would say there's 12 people to choose from. It's a permutation. Order matters, and we're going to pick 9 for a batting order. So if you go to your calculator and you just do 12 permutation 9, we should get that same answer. Yep. Okay, this one, next one. Rob and Mary are planning trips to 9 countries this year. There are 13 countries they would like to visit. So that's a combination. They're going to 9 countries out of 13. So 13, they're choosing from 13, so 13 combination 9. They don't really know which ones they want to go to, but they know out of 13 they're going to go to 9 of them. So how many outcomes for that? It would be 715. Okay. There are 45 applicants for 3 computer programmer positions. Okay, so doesn't really, there's no order here. It doesn't really matter. It's just we need 3 people to fill computer programmers. They're all the same thing. So you got 45, that's a combination. You got 45 applicants. It's a combination, and you need 3 of them. So how many outcomes would there be? 45 combination of 3 would be 14,190. Okay, Castell and Joe are planning trips to 3 countries this year. There are 7 countries they would like to visit. One trip will be 1 week long, another trip 2 days long, and the other 2 weeks. Okay, so the 1 week, 2 days, 2 weeks, that's not really going to be part of our formula. That's just telling us that order matters. It's a permutation because they're not spending the same amount of time in each country. So it's going to matter if you spend 2 weeks in one country versus 1 week in another. So that makes it a permutation. So they've got 7 to choose from. So 7, it's a permutation, and they're only going to go to 3 countries. So out of that, if you do 7 permutation 3, you end up with 210. Okay, there are 110 people at a meeting. They each shake hands with everyone else. How many handshakes were there? Okay, it doesn't matter who they shake hands with or the order. They're just shaking hands with everybody. Takes 2 people to shake hands. So there's 110, and this is a combination of 2. So 110 combination 2 is 5,995. Okay, next page. You are setting the combination on a 3-digit lock. You want to use the numbers 1, 2, and 3, but don't care what order they are in. Okay, it's a combination lock. So you've got 3 spots you have to fill. Order matters here. Even though they say they don't care what order the numbers are in, the order matters on a lock. I mean, you can pick the numbers in any order you want, but you still have to enter them into the lock in a specific order. You have, position 1, 2, and 3 for that lock. So if you're going to choose out of those 3 numbers, you have 3 choices for the first one, 2 for the second, and 1 for the third. So you could really only come up with 6 different outcomes to make that combination lock work. You could do that with a fundamental theorem of counting. That's that principle right there. I just did that one. You could also do that one with a permutation. You could do 3 permutation. So 3 permutation 3 also gives you 6. So you get the same answer. Okay, a group of 25 people are going to run a race. The top 8 finishers advance to the finals. Okay, so they're just taking the top 8. They're not saying, oh, okay, well, he was the top finisher of the 8. They just need 8 people, the top 8. So that's a combination. So you've got 25 combinations. So you're going to do a combination 8. So how many outcomes are possible for that one if you've got 25 combination 8? 1,081,575. Okay, number 9, a team of 17 softball players needs to choose 3 players to refill the water coolers. So once again, they don't care who it is. There's no order that associated with this. It's just 3 people. They need 3 people off the team to go get the coolers. So that's a combination. So 17 combination 3. Type that in, and you're going to get 680. Okay, this one says selecting which 9 players will be in the batting order on an 11-person team. Okay, this one is a combination. The one we did earlier was a permutation because we were actually batting those players. They were actually batting. They needed to have the order. This one is just like saying, okay, there's 11 people and we need to pick 9. It's not actually putting them in order yet. They're not actually doing the batting. You're just selecting which 9 you want to choose. After that, you could change it to a permutation and go to order. But right now, they just want to get 9 players. So this would be 11 combination 9. So we would go ahead and type that in, and we'd end up with 55. Okay, there are 15 applicants for 4 jobs: computer programmer, software tester, manager, and systems engineer. Okay, this one's a permutation. It matters. There's 15 people, but a computer programmer might be way different than a software tester, so order matters here of who gets what job. So that's a permutation. When order matters, it's a permutation. So 15 permutation 4, and you end up with 32,760 outcomes. Okay, last one. A group of 45 people are going to run a race. The top 3 runners earn gold, silver, and bronze. Okay, this is keeping track of place order. That other one where they were just had 8 finishers, we weren't keeping track of the place order. So this one right here, order matters, so that is a permutation. So out of the 45, permutation, order matters. We've got 3 places, gold, silver, and bronze. outcomes for that would be 85,140. Okay, so that's just a couple of examples, maybe to kind of help you get the idea between the difference between a permutation combination or when you could use the fundamental theorem of counting.